Please welcome Bryan to S4 Stage 2.
All right. Good afternoon, everybody. Well, the only constant thing being change. I've recently experienced actually a job change. So today I'm going to be giving my presentation as an independent, not as a representative of any particular organization. But just so you know, actually a matter of a few days ago, I joined Accenture as one of their principal directors. So Dale was very, very patient this year. I had to make some changes, and actually, as we'll talk about here briefly, it was about 96 hours ago, I even had a change in the way of thinking and the way I wanted to work through some of this. So some of this is a bit in flight. So today I'll be talking a little bit about critical attack flow modeling, or why Aquaman sucks. So bear with me a little bit. So this is a little bit about me. Obviously, you can read that. The main thing I wanted to point out is a couple of weeks ago, this is a longtime friend and colleague of mine. He and I have been working on some similar subjects for a while. And we got together and said, hey, look, let's share some ideas. I submitted some stuff from one of his talks he's giving, I think, today, as a matter of fact. And he shared some information with me. So I went ahead and named him as a contributor to this as well. And I look forward to doing some more work with him in the future. So that's putting that out. So this is funny. This is something I said, I've been doing this for a long time now, since this was S4 was 20 of us in a room and 20 of us on a chat channel. But this is something I said years ago. I'm an IT person, okay? I always said it, made no bones about it. I've learned engineering over time. But this is something I said years ago, and like I said, the crowd goes wild. Cybersecurity for industrial or for OT is an engineering problem that requires an engineering solution. It always is kind of painful to learn how to choke on your own BS, though, sometimes, right? And to realize I didn't need, even when I said this, I didn't know really what it meant, right? So does this sound familiar? And now I will also put it in here. I've always worked as either a vendor or a consultant, never as an asset owner. But I've had this conversation, and I bet a few in this room have had this as well. Security consultants, I could use this attack to open up a valve and cause a lot of trouble or a rupture on the pipe. Well, the engineer just goes, well, I would just do this. Well, okay, well, I would turn on a burner and I'd do this. And the engineer would go, well, I would just do this. And we have this conversation back and forth, and then I go, wait a minute, why haven't you then, right? It's like, yeah, they know what the problem is. In fact, actually, this is what I've come to learn and understand is that when we make the problem real to the engineers down there, when they understand the threat is real, the solution to it or the thing to do to address it usually is it usually is a fairly natural consequence of it. Like, oh, this is what I would do. Okay, great. Why haven't we done it? Fundamentally, I've been saying this for years about engineering problem. However, we still have not connected to the engineers in many ways. So lots of different studies out there. We have ChazOps, HazOps, attack trees, layer protection analysis, threat modeling, gap assessment, penetration test, PHAs, cyber PHAs, kill chains. Okay, goes on and on and on, right? We hear all these all the time. But I don't know about you guys, but one thing if I look across an organization that's done most of these, they almost never agree. There's a lot of inconsistencies, and it's like, well, what do you do when? For example, if you're doing a PHA on a greenfield build of a plant, every single thing you find on that process hazards analysis is at least $30,000 US to fix, at least. So when you're going through and designing a plant, the last thing you really want to do is put a whole bunch of additional controls in there that's going to cost a whole lot more and potentially delay a startup or cause all kinds of problems. So if you drop a security PHA in and it comes up with a bunch of stuff that the PHA didn't, you can see where a lot of people are probably going to have some angst and consternation about it. So really, again, my problem with most of these, look at a risk document. And I'll go to the second point first. It's kind of like when you drive a new car off the lot, what happens? It immediately loses a whole bunch of its value, right? And I look at things like risk studies and even cyber vulnerability assessments and a lot of those types of things. One of the challenges I see to them is they're too static in nature, right? They are old as soon as you create them, and nobody really goes back and updates them with any type of regularity. They're just updated every few years, right? So, and then again, you'll see studies, one thing's done now. Somebody does a gap assessment, then they do a risk assessment, then they do a CVA. Never the twain shall meet. A lot of times there's problems with the document. So there are a lot of times they're check the box. The main one to me is they don't adequately address CyberPhysical. And if you guys have heard me speak over years, I've spoken a lot on CyberPhysical and the intersection between safety and security. And this is the biggest problem. It doesn't naturally create a motivation to action that somebody goes, we really should do something about this. Findings are not correlated and can increase costs, delay startups, and they don't account for engineering mitigations that are out there. Okay. So this is what I like to boil it down to the simplest things possible. In industrial cybersecurity, And I just randomly pointed something on the screen here, just so you know. But it's like fundamentally, OT cybersecurity should be able to say, what happens if we mess with this one little component, okay? What type of access is there to it? What's its function? What is the risk associated with opening or closing or turning on or erratic start, stops, delays? We need to be able to answer that question for every component that's out there. So obviously, when we talk about cyber-physical, we talk about the intersection between safety and security. All right. So challenge. This is what I've been really trying to work on for a while now. This is really kind of coming over a period of years. I wanted to create a better model, dynamic and extensible model and framework that creates a unified cyber-physical threat model, something that we can say, hey, this will all work together. Should be extensible and dynamically update based on evolving and additional information. So if your honeypots start lighting up, if your IDS lightens up, or if you do a new CVA or new vulnerability information comes out, right, you should be able to go back through and update some of your base assumptions and see really quickly how that changes your overall risk environment. Okay? Doesn't replace existing studies. I'm not going to change anything on this, but what I really want to do is say, how do we augment what we're doing so that they make more sense? And should naturally assist in the selection of preventative, detective, and reactive controls. Those are the three types of controls whenever I'm looking at something. You have a control that will prevent, a control that will detect, or a control that will help you respond and react. So if you can't do a preventative, what do? Maybe a detective control. What do I mean? Like, so let's say, for example, I use this one all the time. I don't want a password on the HMI that controls the boiler, right? I don't know about you guys, but I type my password wrong 3 out of 5 times anyway. Now put somebody in a stress condition where something's going wrong inside of a boiler and they have to log into an HMI, probably not a good idea. Overly simplified example, I know. There's other kinds of options out there, but it illustrates the point. In this case, I can't put a preventative control to stop somebody from logging in. I need a better detective control, something to say who was in the area at that time. Just as an example. So you should always have a good blend of preventative, detective, and reactive controls for everything that you find. Okay? So that's where I started working with a concept called a critical attack flow modeling for OT. Okay. All right. There's a couple little nuances here that aren't really obvious at first. So if you look at the most basic risk equation, it's very simple. Risk equals likelihood times consequence. Right? Now, if we go look at the safety side of the world, one thing I love about industrial cybersecurity, we already know what the worst case scenarios are. They're documented. They're on the HAZOP. They're on the PHA. They're on cause and effect diagrams. There are things out there that have been done as we built this plan. So we already know what those worst case scenarios are. There's financial modeling behind them. We don't have to go out and create anything new. We know what they are. Now, in cybersecurity, fully admit, we do have other things that we look at as well. But I always say, when you're starting a project from the cyber side, don't create anything new right at first. You only want to go with what you already know on paper and everybody's agreed to as a documented and verifiable hazard to the process. So it's similar to the kill chain concept, and it treats cybersecurity very much like a supply chain. So I always say, look at the 6 walls of the plant. On the left-hand side is all of those entry points into your system. These are the engineering interfaces, like engineering workstation. These are web interfaces, anything that's forward-facing out to the web, engineering workstations, field devices, anything you can think of. These are entry points into the system. So the first thing we look at, and if you look on the bottom left there, is the likelihood of attack of those entry points. What's the attack surface look like? What's the attractiveness look like of that target? Then you move into the fact that all those entry points will give you access into a system, right? Now, this is where it gets a little bit weird because normally we just say risk equals likelihood times consequence. And again, safety's already figured out likelihood for us pretty well. And what? Anybody know on the safety side? What do we measure on the safety side for likelihood? Like the probability of failure on demand, mean time between failure. These are things we can observe and measure over time, and we can have a fairly good measurement of what is the likelihood of occurrence of a particular type of event, right? The consequences are also documented. What we haven't documented and what we don't understand as well are what are the non-deterministic or the deterministic threats from a cyber perspective look like. That's the piece of the risk equation that we need to answer. What's the likelihood somebody is going to use a cyber attack to create one of those hazardous conditions, okay? This is where it starts to break down, though, because again, if you look at right now, let's say I have let's just do a recipe inventory control system or batch control system, right? And I know that I can gain access to that system because I've got a third-party vendor-managed interface that allows me right into the darn thing, right? Well, now I can go in and I can mess with the recipe. I can change the values. I could potentially change the way something's going to be processed, and maybe try to set up and poison a batch or cause a problem in production, right? my favorite was I was working with blended cheese many years ago. And if you put too much sorbic acid in blended cheese, you don't make cheese, you make Quickcrete, right? And it's a $250,000 plus clean in place operation. And I always liked using that one from a cyber perspective. It's like, what happens if I just mess with the recipe? I don't actually mess with the control system itself. What if I just change those inputs, right? And I can create all kinds of problems. So now, though, if I gain access to that system, does that then mean I will definitely make Quickcrete? Well, that's where all the rest of the controls come into place. Well, maybe there's some type of other system out there. And if we want to get into more of the crater factor industries, looking at like turbine gas compressors or hydrocrackers or things like that using oil and gas or liquid natural gas pipelines, understanding that, yes, just because I can close the demand valve and the suction valve does not mean I'm going to be able to put it into a surge condition, because there's what? There should be a machine over speed protection device of some type in there. Right? That's where we need to understand. Just because I can gain access to the system and even attack the system does not mean I'm going to get to the next level. So I model 3 things, and I keep them separate. We'll go into this, talk about this a little bit here. 3 things to keep them separate. The likelihood of the exploit for a given system entry point. That's all the way on the left-hand side. What's the likelihood something's going to be attacked? Then, what is the likelihood that that access is going to give me access into a system and that I would actually be able to gain access and gain control of something based upon that access, right? And just because I have that access, this is the cyber-physical piece that comes in that nobody's, well, I shouldn't say nobody, but this is the cyber-physical piece here where we really start to need to understand this, because just because I can actually manipulate that system, what is now the likelihood that I can actually create the damage scenario? So likelihood to me is now evaluated in 3 different steps. What this gets us through is this helps us with the problem of saying, okay, wait a minute. I put in a firewall, so therefore your attack is no longer valid. Well, wait a minute. You know what? I know like SIP reset, Modbus stop commands, DHCP or DNP3 broadcast reset. We have those protocols allowed anywhere for safety reasons inside of a plant a lot of times. So just because you put a firewall in does not mean that I cannot use the actual control protocol itself to manipulate a device. Still have the issue sitting out there, right? Or let's say I look at let's say with the turbine gas compressor, and I have a machine over speed protection device in there, and so it's like, hey, even though I may try to close the demand and the suction valve, I'm not going to create a dangerous condition, because that machine over speed protection device, that physical control now, or that physical safety system, it's going to stop that attack, right? So just because I can do the attack doesn't mean I'm going to get the damage. And that's why I've started really separating this out into 3 key elements. So some examples here, some factors. Engineer safeguards and other protections that could prevent attacks from creating damage that aren't really factored in. So example 1, an attacker can force a valve open, but an emergency relief valve would mitigate any damage. All right? I always say, like, I did a presentation years ago about hacking distillation columns. I don't care what you do to that distillation column. If the emergency relief valve at the top of that thing is sized correctly, all you're going to do is make the flyer stack pop. You're going to burn a bunch of money. You're going to make a bunch of pretty lights at nighttime, or something. But that's the worst you're going to be able to do, right? Okay, from a physical explosion scenario. Example 2, attacker can close demand and suction valve. I'm using this one to a gas compressor, but will not be able to create a surge based upon machine over speed protection. Number 3, attacker finds the safety builder. This is where this cyber-physical comes back into play again. Let's say, however, let's use this turbine gas scenario, and the attacker finds that you have the safety builder application located on the same network and same component as one of your engineering workstations. Now the attacker has access to not only the demand valve, the suction valve from the cyber side, but they also have access to the protection system, and they can either disable it or they can manipulate the safety instrumented function so they could still create the damage scenario. And this is why I've started breaking this out a lot more. Example 4, network and malware-based threats are rendered ineffective due to physical controls, but damage scenario can still be created with insider threat, fraud, and collusion. Okay? This is where, again, one thing I would say about risk. You never really remove risk. And when you do a risk study, you have to consider unmitigated risk before you do anything else. You never truly remove risk. All you do, you can mitigate it, but all you do is you take it from one column and you put it into another one. And a lot of times people forget that piece. They go, oh, I put this control in here. I don't have to worry about this anymore. I said, well, now you have a fraud and collusion problem, and you need to understand that one as well. You have an insider threat problem. Other ones you need to be considerate of. So I wanted to be able to build a model that would work through all of these. I've been talking about likelihood a lot, so let's just go ahead and deal with the white elephant in the room. Likelihood is the Aquaman of cybersecurity. It sucks, right? It's hard. Nobody has ever come up in cybersecurity with anything. Anybody here have a really good measurement for the way they do likelihood, in their opinion? Anybody? Bueller, right? Anybody? No. I've not seen one yet. But we're going to get back to that here in a few minutes. I just wanted to go ahead and deal with that. We're going to talk about likelihood in a minute. So let's talk about it. Best way to illustrate is by example. And again, please bear with me here. Obviously, I don't want to use any customer documents or anything like that. So what I did is I happened to have some example PNIDs of a turbine gas compressor. But I have CNEs, cause and effect diagrams, for a sample hydrocracker. So you're going to have to, imagine, if you will, here with me just a little bit. But the important part, and I know it's an eye chart, is what I found. I can use this model as a gap assessment, as a risk. I can use it in different spots. But what I have found is, let's go to the lowest level possible first. Go straight to the cause and effect diagram, okay? Or cause and effect chart sheets. You go straight into the CNEs at this point, because right there is all the information you need. You got the PHA that tells you what the hazard is, what the consequence is. You've got the CNE that tells you if you open this valve, if you turn this on or turn that off. All of that cause and effect is already modeled out there for you. Again, leverage the tools that you have before you start creating a bunch of new stuff. So what I've done with something like this now is I say, all right, fine. If I'm worried about this particular exploit chain, opening a valve, closing a valve, manipulating the system, go to the CNEs. Now I know what that is. Open this valve. That's what it says in there. I can connect to that. No, so okay, now what's that connected to? That's connected to this controller. That's connected to this HMI. That's connected to this switch. That switch is 4 levels behind, or 2 firewalls behind, or anything like that. Understand then, that's the kill chain aspect of it, of working backwards and saying, what is the likelihood somebody is going to exploit all those controls to get all the way into that device and create that consequence? Okay. And this for me is what it looks like. So I've given you attack flow 1. HMI RDP session is opened up. Likelihood of exploit, and this is an example here. And please understand that when I've done this is actually quite a bit larger, so these are very simplified. But the idea here is pretty simple. You say, what's the likelihood of exploit? We look at the HMI. HMI's got a vulnerability on it, or it's got RDP turned on. It's only one switch behind the main firewall, and we found 2 open ports. So therefore, we think the likelihood of exploit, and I'll show you likelihood in a minute. We think the likelihood of exploit in this particular scenario is 38%. It's a measure of 38, right? System access. Well, it gets you into the valve control system. What are the consequences? I could manipulate. What's the likelihood I could open the valve? Anybody ever tried to just use network traffic to open and close valves? Or like we did it years ago by reading partial stroke test while we were trying to read what the packet structure looked like on partial stroke test for safety systems, right? Found out it was actually not as easy as we thought it would be for us to be able to artificially open or close a valve just by replaying traffic onto a network, or at least it shouldn't be, right? Now, I know that's not universally true. But anyway, what's the ease of exploit on this one? Well, if I have access to the HMI, what is it? Point, click, point, click, point, click, right? So the likelihood is pretty high. Ease of exploit is pretty high. Then, so we know what the risk or loss is. In this particular case, I said $2 million. It's probably pretty low for almost everything out there. And then what's the consequence? So just because I can gain access to it and open or close, now how complex is it to turn that into a maximum damage scenario? And actually, so I say, what is the consequence exposure? And then we come up with a raw exposure of $1.2 million. The risk is $296,400. This is just me doing some very simple math to consolidate this down for the ease of demonstrating. But what happens if we now change likelihood? So likelihood, we have a new exploit that came out, or somebody found that this HMI is sitting out on Shodan right now, right? Guess what? The likelihood of exploit just went up a whole lot. However, that probably doesn't change the complexity of getting in and opening or closing a valve, and it probably doesn't change the consequence associated with it. Still the thing. The only piece that went up in that was the likelihood of exploit based upon that information. Similarly, excuse me, let me take one step back. And what you should be able to do here is look at the delta of that and then reprioritize all of these attack flows based upon that. So let's say, for example, again, you see that in your honeypots and your IDS, people are starting to attack a particular exploit, or you're looking for a particular exploit, and when they see that, what do? Hey, guess what? The likelihood just went up. Now, based upon this information, what are the attack flows I need to keep an eye out for the most? And that's why I like having this, so that we can actually dynamically update this and understand what changes. Now, how do I change my focus based upon this during the day? What really matters to me now at this point? That's the important part, okay? So let's go in here. We say, however, we found that the ease of exploit out there is actually higher because we thought, based upon our gap assessment, we thought this was very difficult. But when we actually did a CVA, or we did a network packet capture analysis and replay and a pen test, we found out this is actually a lot easier than we thought. So guess what? Likelihood just went up. Consequence just went up. You should be able to see how all these things are going to change. Okay? Now, again, so let's go deal with that white elephant now. Because, again, I admit likelihood sucks. However, I mentioned earlier, I've been a vendor or a consultant for my entire career, really. But one of the things I've really learned a number of years ago was take what your biggest, this is for all the new folks in the room breaking into the field. It's a great thing to learn early on. Take what are your biggest impediments to success, what those things are that cause you all kinds of difficulty, and find a way to turn them into a strength. And what do I mean by this? So one of the examples I've had, probably you guys, so a lot of you have had this in this room, hey, what happens if your customer can't supply you accurate documentation? Well, that increases the likelihood you're not going to find certain things. You're going to have errors and omissions in your report and those kind of things. So rather than me just totally accepting that risk, I would rather involve the customer, and now we can work back and forth, and they can understand if you can't supply the documents, or if you supply us documents that are only 20% correct or have errors all in them, this is what's going to happen to you as a result. These are the things that are going to happen. These are the additional risk you're not aware of. Turn it into something that you can actually evaluate and work with your customer on, right? Or inaccurate or missing architecture diagrams. Same thing. Hey, I might have an unintended consequence. I might end up on a system or an IP address I'm not supposed to be on because you provided it to me on a sheet that wasn't correct. Right? So rather than accept that risk outright, work with the customer and they understand if this is going on and you are actually responding to a malware incident, this is going to take you a lot longer to respond to. You're not going to be able to find the components out there. This is going to increase your support cost. Turn it into something they can use. Or my favorite one is, I've had this happen too many times. They're like, hey, we need a span or a mirror port turned up on a switch. And it takes them 8 hours to do it and they get it wrong the first 3 times. And I'm like, okay, let's understand that now you're dealing with a malware attack scenario. You're telling me it's going to take 8 hours to figure out how to isolate that on the network. This is how much further this exploit is going to go during this time. So again, just a couple of examples here, and I just wanted to make sure I highlighted that I want to turn this into an ally. Same thing I want to do with likelihood. I want to turn that into an ally. This is what I really started, to be honest with you, working heavily on about 4 days ago now. But this is the way I've been working on it for a while. It's to say, okay, fine. What are things we're looking for? We know that lateral movement within the network is going to be one of the high-risk exploits. Okay, fine. So let's figure out what are the Windows system log event IDs associated with the MITRE attack framework. How many of those are relevant to that particular threat scenario? So if you got a whole bunch of them are relevant, well, guess what? That's probably going to increase your likelihood. The next piece to this is what I like the most is now that I know what those attack IDs look like and those system events look like and the network events look like, I can then build detective rules into my intrusion detection and SIEM systems based upon that threat. This is why I'm starting to really like this model. It should be a natural consequence that goes, I'm looking for these 8 IDs. I can write things that actually check for these 8 IDs, okay? Or I find out that the attack surface is very high. It's got a huge number of CVEs out there that I can't patch, or it's got a whole bunch of open ports and services that I can't close. Guess what? That increases your attack surface. And I like to go back to my military analogy. I worked in Intel back in the in the 90s, and one of the things we worked with a lot was called these counterintelligence matrices, right? That you get one piece of it, you get a fingerprint here, you get a face here, you get a picture, you get a name here, and you start building this confidence up over time. I want to be able to do the same thing with this, which is said, hey, maybe we do a high-level gap assessment and we only do the high-level system mapping. But later, we do a CVA, or later, we do some other type of network discovery, and we get more information. We should be able to update this model and see how it changes and accurizes over time. The second thing on the likelihood side, I've really started borrowing that military analogy again, the concept of high value versus high payoff targets, right? What would be a high value target to an attacker? What would be a high payoff target to an attacker? Don't have a lot of time to get into those today, but I've started building the attack surface models based upon that. And then, obviously, identify mitigating cyber controls. This is where, again, looking at the different pieces there, what are the cyber, preventive, detective, and reactive controls I can put in place, or what's a physical control? This last two are the ones that are the most important here to me, because you don't ever really short-circuit it. Oh, I would just put this in and it stops everything. Not necessarily. This is where, in order to understand cyber-physical, it's very, very critical that we get that last category right. Now, if you're trying to look, by the way, if you're trying to look for divine purpose or be able to figure out the math on this chart, I'm going to tell you right now, you're wasting your time. I just did this for an example, all right? But what I've built here, what I've built out in a much larger form is I do a weighted average of the various pieces out there about attack flows, attack IDs, and attack surface, high-value targets, high payoff targets, different controls, and I do a weighted average with them. Anybody here done a lot of risk management studies before, or risk studies, risk analysis? Yeah. What sucks about those a lot of times, too? The first round, what happens? Are the numbers believable? No, they're ridiculous, right? And everybody laughs you out of the room. And where, I don't know, Jim, you and I have done these, so it's a good example. Where somewhere around, revision 3 or 4 that people finally start to nod their heads and go, okay, we can buy into this, right? That's my experience. We've seen a lot. We have a few war stories on these. And the same thing happens here. You need to be able to say, how do I get this into, oh wait, if I tune and I tweak these numbers a little bit, what do I get to a believable set? So this is something I really started working heavily on a few days ago, so I expect to do quite a bit more on it, but the concept is I ought to be able to plug different values and see how they change and get to a normalized model over time. And I can think of all kinds of ways to do it, but anyway, so some additional scenarios. I'm not going to go through these because I only have a few minutes left, but really to understand, in a boiler, what would be the different things you could do to a boiler? What would be the different things you could do to a gas compressor, or a steam turbine, or a generator? What are some of these different pieces in here, and what you need to consider from both a cyber and a physical perspective, and never get caught in the trap of going, I put in a cyber control, it's gone. No, it's not. I put in this physical control, it's gone. Not necessarily. It may have gone to another area. You need to be able to model both, and people understand these are how these two pieces would actually work together. Okay? So output from the approach, this is what I like the most about it. Once we come up with a better method for calculating likelihood, and we're kind of getting there, some of the examples we've done with this so far and what I've done. In fact, actually, we've had some interesting days geopolitically here in the last few weeks. And I imagine a few folks in the room, like myself, got some of those calls going, can you help me figure out what in the world is going on? I've had actually an opportunity to apply this model directly in the last couple of weeks to really go through and say, all right, you know what, hey, what you're seeing right now is not that critical. You're seeing people trying to gain access. What you need to be looking for next, though, and they started seeing them, was, hey, there's these RDP probes going. There are these Citrix things are getting popped. Now you need to start looking at this system. And we were able to apply this very, very quickly. And I was able to say, all right, now, this doesn't matter, but this is what will matter, and this is what you need to start watching for. So, for example, do a PCAP of a partial stroke test, or opening or closing a valve. Write that into a snort rule, right? Figure out what those different event IDs you're looking for that are relevant to the attack flows from the MITRE ATT&CK perspective. And I've really just I've become more of a fan of MITRE ATT&CK in the last year in particular, I'd say. Something we've known about for a while. And then I know obviously I saw Dragos has released some information about it recently on the ICS. So it's getting a lot better. There's a lot of good information out there. But find out what those event IDs look like, write rules around them so that now you know what events based upon the attack flow you care the most about. And when those start hitting on your IDS systems or SIEMs or on your analysis, hey, that probably changed the threat curve. We need to look here as opposed to looking here, right? Writing DPI, this is one of my favorite ones. So looking at some of our industrial firewalls, some of them have deep packet inspection capability, like looking deep into the Modbus protocol. Well, hey, you know what? If I know that issuing the Modbus stop command or a DNP3 broadcast reset could cause all kinds of issues, why not write an alert and a rule that says, if a device other than this one or on this side of this VLAN, if anything else issues that command, generate an alert. Send a signal. Let somebody look to say, hey, somebody's doing something they shouldn't. You may not be able to stop it because of safety, but you at least want to say, from a detective standpoint, I have generated an event that somebody is now going to go look at. The key is get context of the 6 walls of the plant. That's what you have to make all of these things work together. Okay? And then identifying additional engineered safeguards to mitigate specific attack flows. But again, just because you mitigate it physically doesn't mean the cyber aspect's gone. You still could do all kinds of things by misdirecting operators, social engineering, fraud, collusion. You cannot ever just go, we're done. You need to understand how things change based upon the different controls you put into place. So, okay. With that, I've got about a minute for questions, roughly. Any questions? Man.
Sorry. So I come from a functional safety background,
Yep.
and I've done a lot of this risk assessment. When the likelihood is the problem for me, because what I've seen with you have a risk matrix that's based on order of magnitude increases in likelihood, whether it's 4 by 4, 5 by 5, 20 by 20. The difference here is with this, you have events that you identify in the physical world will happen because of equipment failure or the process uncontrolled. In this case, it's literally somebody with an intent to do it. And so when you start talking about likelihood, I like the idea of ranking them, of trying to calculate a score based on the ease and the inputs that are in there, but I don't know how you turn that into to like a corporate risk standard, because the likelihood scales are not the same, because you have an actual adversary trying to line up the holes in the Swiss cheese model, if you will.
Right, absolutely.
And so that's what I'm trying to figure out is, when you're coming up with quantitative numbers here, how are you?
Yeah. So, like I said, and part of that is again evolving a little bit in the last little bit. And one thing that might help is in the last year in particular, I spent a lot of time looking at more of the incident response side. So my brain is keyed a little bit more on the incident detection, incident response side in some way. So far I've applied this model a lot more just upon what event IDs are we looking for to give us early indicators of attack and those kind of things. So I've not really finished some more of the like you said, kind of that qualitative analysis. However, what I have seen kind of showing that on there is going, I've been putting it to dollars, but we can do it. The safety world did that. They picked 1 through 5 for a lot of good reasons, right? And the security world kind of needs to do the same thing in many cases. But that said, I still need to have a way to be able to rank things a little bit better. And that's what I'm trying to be able to do, is actually sort those flows. To me, I'm just trying to sort the flows out. Well, which one am I looking for, right?
And that's what I agree with. That's what I really like about that is actually trying to say which is the most likely and being able to track that. Right. It's just when you start talking about assigning likelihood numbers and stuff within the realms of a typical corporate risk matrix, they don't work really well, because it's not gonna happen. It's someone with the right skills.
And there again, I think the way I would address that now is we're not replacing those studies that are done. I'm providing a model to understand them better, right? That as we look at that and we know it, that as you build and layer this on, hey, this should become, to me, the outputs of this should become what you do for prevent, detect, and respond inside of your environment. And being able to say, hey, this is what we understand. And if nothing else, if you see something, the way I would handle this right now, if somebody wanted me to go back and look at a risk study for safety side done today based upon this, I would go through a few of these scenarios and I would say, does this change any of our underlying assumptions? Because we found out there's a lot more risk associated with this event than we thought, right? And that's the way I would do it now, is go, do you now accurize that earlier model, because we see that there's a much bigger attack surface or a much higher likelihood based upon the threat flow modeling that we've done. That's the way I would address that today. So
that makes sense. Thank you.
All right. Anything else? Okay. All right, Alexa, well, thank you all very much. I appreciate the time this afternoon, and I'll be around the show for the few days and tonight, so I look forward to speaking with you.